Hi, this is Open Up Resources, Algebra 1, Unit 2, Lesson 3, the name game. We are going to practice what we've been learning using representations to determine if a function is discrete or continuous, and then we're going to determine the domain of function, and we'll actually do it in the proper notation, the set notation. So in today's lesson, you're going to play a game with a neighbor. You and your partner are going to have your notes. We're going to use that as our game board and a set of cards. Each chunk of 4 has 4 smaller squares, and different information is given in the first square, the top left. So in one of the squares, you're going to have to produce some kind of information, but the other 2 squares will come from finding a match with the deck that you're given. So by the time you finish, you'll have filled in all 4 squares. And so the top left has the given function in some format. The top right has the domain of the function, whether it's discrete or continuous. The bottom left has another representation of the function, and the bottom right is the type of function and the type of growth. So make sure if you have, here's the types of functions, linear and exponential, and remember linear functions, the type of growth is a common difference. Exponential functions, you can call it a growth factor or you can call it a common ratio. So let's go ahead and fill in our chart. So the first one, doing together, if you notice, we have the function is a equation, and we can see that it's linear. And so let's first just look through our cards and see if we can figure out one of these representations from it. Well, in this case, we have the examples. So these are the example cards. And actually, I'm a little disappointed that this one is actually incorrect, but we are going to copy and paste it anyway and put it over here. Just, oh no, undo. Select, here we go. Make it a little smaller so it fits in here. So the bad thing about this one is it's not actually accurate, which is kind of annoying, but we're going to go ahead and just use this graph so that we can use this graph. Zoom in just a little bit for this. Okay, so I know I need to start at 3, which is where it started, but I need to go down 1 over 4. So my next point would actually be right here on that. And then I'd go down 1 over 4, which is right here. So my graph would actually be like this. So that is the graph that we want to use for this one. And we can actually extend it the other way as well. Keep it as a straight line, up 1 over 4. Up 1, I can't. It's really hard to see this on my tiny screen. Okay, there we go. All right, so the pink one is actually the one we want on here. Okay, and so then the other example happens to be our type of function and the difference. It's continuous, linear, and it's over here. So let's go ahead and take that one and put it over here as our type of growth factor. Ooh, we need to shrink this dude down. Okay, here we go. So what's missing now is the domain of the function. And so then my domain, I'm going to shrink that just a little. Get this to go down maybe. Okay, there we go. My domain then, if I notice there's no limitations on my equation. My equation means I can put any x value in and I'm going to get a y value. So my domain is, my x is my variable. I'm going to define that. And x can be all real numbers. And I can see that it is continuous. It's not a oh my goodness. The other type, it's explicit. It is not recursive. There we go. All right, next one. So number 2, I'm going to go through on here and I'm going to look and see if I have anything that looks like I have the first term is 1, and then I'm multiplying by 2/3 each time. So if I go to my cards, oh, here we go. I actually have this one right here. So it looks like I have a function. Oh, lost it. And then I'm going to undo. Let's get that to fit in here. So there you've got the proper explicit equation. Type of growth factor or a domain. It looks like it's going to have to be discrete because I'm looking for discrete, and a growth factor would be 2/3 an exponential, right? Because I'm multiplying. So as I'm going through my cards, I'm going to see that G is mine here, and I can use that as my growth factor. Got all my little clicks here I've got to do. Okay, and so you can glue these on, cut them out. So now I'm missing my domain. So now I've noticed that if I start with 1 and I have to do whole numbers, it's discrete, then that means my domain is going to have to be, and let's see, my variable this time is n. So n is, and I'm not using any negatives, so it has to be natural numbers. So I'm going to do that crazy n. All right, so as you look at these, I want you to pause before you move on to the next one and see if you can find, let's see, get my page here, see if you can find something, one of these that will match it. So go ahead and pause, see what you can find, and then I'll show you the answer. Okay, so if you've gone ahead and looked through them, you'll see that you have a domain on this one. It's letter O. And if you go over here, how do we know this is the domain? Well, we're looking through here, and it looks like on this guy that this has a negative 130 on here, right? We're going from negative 130, and we'll guess it's a 0 at this point. I don't know. As I'm looking through, I notice I have this story that goes with it. And so I'm going to use this story. A diver goes underwater, and the pressure, every 10 feet, it's getting a little deeper, a little more pressure. And so going underwater, this would all be underwater. So 0 would be my highest. So that works for that one. Okay, so now I need the type of function and the growth factor. So I am going to go ahead and type this one in, at least my function. My function is a continuous because linear. Because if I'm looking at this, it increases 4.4 pounds every 10 feet. So that sounds like a slope to me. And actually, how I'm going to solve this then, when it comes to the common difference, because if it's linear, if it's down, every 10 feet deeper. So the negative, it doesn't really matter which one the negative goes with. But if I have 4.4 divided by negative 10, so it goes up 4.4, for every 10 it goes down, then I'm actually dividing that by 10, which is negative 0.44. And so if I would go through and work through some of these, I would see that every 10 I go down negative 0.44. Or each one is going down. So I go down 4.4 every 10. All right, next one. See if you can find the ones for this. Go ahead and pause. I'm going to go ahead and work through here. If you're checking yourself, one representation, if you're looking at this, it's exponential. One thing you can do to try to figure this one out is click on these different, or look at the different points that are on here. So I see that I'm just going to text box these points because it's hard to write them on here. Let's make them 10. So I see there is a point at 0, 1. There's also a point at 0, not 0, 1, 2. I see there is another point at 2, 4. And I see one more at 3, 8. So you can just kind of look at those different points and see what you're doing. So to me, that's exponential. So I'm going to look for something that has an exponential show on there, and continuous. Okay, so none of these really say exponential, but I can tell that as if you're going through here, if I kind of look at here, here's a 0, 1, 2.5 is 4. Don't know if that's what we got on our little graph here. Looks to me like 2 is 4. That one's a little sketchy. Might be a check on here. But the one that does go with it is J. Seems like the accuracy might be a little sketchy on some of these. So this one is going to go here. Oh, what did I do? Here we go. Select. Let's make this a little smaller. It's the one that's supposed to go with it. And then we see that our domain is continuous and it is all real numbers. So we're going to put that one over here for our domain. Get that out of the way. There we go. And so I can put that in here. I said you're cutting and pasting. So that means we need to have the type of function and the growth factor. So when looking at this, I see that this is a continuous exponential, and my common difference, or not common difference, my growth factor or my common ratio, whatever you want to call it, is 2 when I look at my graph. And this one's a little off. Oh, 2.5. No, I don't know. It's supposed to go with that one. This one's got a couple little errors in there, it looks like. All right, next, you're looking at this function. Oh, I better zoom out a little. Oh, wrong way. So you've got another, looks exponential-ish. Again, you can plot a few points on there to see what you get. Go ahead and try to find it. When you're ready, the ones that go with it. So if you went and plotted the points, you're going to see that it's not linear or exponential. There is no constant change factor for this one. Growth factor. So this would be a neither. You got an example of a neither here. And one reason why I call this a neither is notice how it stops to some degree. That's one thing to kind of check. I mean, our domain doesn't have to be all the way through. But if you look at the points, it's obviously not linear. And if you're checking some of these, it's not quite, it is not quite exponential. Because if we look at our points, I see one at 0, 1. So here's kind of our 0, 1. And then I see another one at 1, 2. So it starts off thinking it might be exponential, but then 2 is 5, and that throws that off. And so if we go back and look, we actually can make a table as our representation because we don't have a representation, but we are only greater than or equal to 0. So that is our domain in this case. So let's get back to this guy. There's a lot of semantics on this one with our copying and pasting, huh? Okay, so there's our type of function and that. And so our other representation, I'm just going to go ahead and list my points, my table, my x, and I'm just going to do my big line, y. And so I have 0, big line, 1. My next one is 1, big line, 2. And then my next one is 2, big line, 5. Okay, so I kind of made my table that way. All right, 6. Again, try this one out first. Pause. Okay, for these, hopefully you can also do all these in any order. You don't actually have to go in the order I'm going in because it might be easier to figure out some of these than others. But your other representation is right here. So we notice if we start with 500, this is the only one with 500. So we're going to put that one in here. It's our other representation. And then what else do we have finding here? I see we've got a domain that involves W has to be, so our answer is 50, but if we're, or 500, but if we're going by tens each time, we can't have more than 50. Otherwise we run out of candy. So, we're going to go ahead and make this our domain. Here we go. There. This out of here so I can move this. All right, so that's our domain box. And so then we need to fill in what the type of function is, and in this case, it is a common difference because we are subtracting 10 each time. So this is discrete linear because we can't actually have half a candy for this case. And common difference is -10, right? Because that's what we're doing each time. All right, on to the next one. Or if you're jumping around, that's fine. See what you can do for this. Go ahead and pause. So 7, we have a slow exponential. So we actually have the graph given to us. And if you're looking, it starts at 40 and is decreasing each time. And that's what's going on. I clicked on the page. Whoops. Okay. See. Oh, I'm not hitting save. My goodness. Capture. Okay. So if you notice, we start with 40 grams and it decays at 5%. So it has to go downhill. And so to do that, we don't have a whole lot of space for this graph. So we're going to have to make it kind of tiny on this page anyway. You can tape yours on however it works. And then, so we're looking at a continuous and we're looking at exponential. So let's see what else we can find. Continuous, notice it's going to stay above 0 because it can't decay into the negatives, right? Either you have some or you don't. And so once you run out, it's got to stop at 0. So our domain is anything bigger than 0. And we could probably tap it out at 40. if we want to be more specific. All right, so our type of growth is continuous, and this would be exponential. But then our growth factor, or common ratio, is, and what are we going down each time? If it decays by 5% each time, then that means it's 0.95. I'm going to put a 0 in front so there's no confusion. And just for purposes of why this works, you always start with 100%. And if you subtract 5, then your answer is going to be 95%. So percent minus 5% is going to be 95%. And that's how you write the percent as a decimal. All right, number 8. Go for it. Pause. All right. This one, we have our representation. We see that we're doubling each time. We look at that, it's 1, 2, 4, or half, 1, 2, 4. So it's a exponential. Here we go. And then what else we're looking for? 1 second. We're using W to represent our set of numbers for this one. So we're going to go with it because it's not all natural numbers because we have that 0.5 in there, but it's whole otherwise. So we are going to have that in there. We won't really use W much at all. I probably would have listed all the different numbers at this point, or at least just what's on the graph, because that, or we'd have to say real numbers just because it could be partials. So I don't know as if I would agree with the W piece, but that's what they did for it. All right, and so that means we have a discrete exponential, and then our growth factor or common ratio is, and we said we were doubling, and right here, common ratio right there is in our equation on that one. All right, so this last one, you should have whatever's left, right? That should be it. So if you want to pause and make sure these are correct so far, great. Otherwise, I'm just going to keep going here. So what we're left with are K and D. So if we read our, actually, no, I'll just go ahead and keep that on there. If we read this or look at this, it's linear, it is continuous, and oh, I'm still back here. It's linear, it's continuous, and it's all real numbers, right? So that does work for that guy. All right, so then what's left? We notice we start at 40. There were a couple that had to start at 40, and we are linear. We may not have realized kind of what that common ratio or common difference is, but we know that it's going down, and it is not the 1/4 because we've already used that. And so we're going to trust him on this one, that it is a negative 22/15. And then type of function and growth factor we need to fill in. And for that one, we have continuous linear. And our common difference, we know by looking over here, is the negative 22 divided by 15 on that. All right, that is all we've got for this one. If you want to practice by doing more representations for each of those, go for it. Otherwise, you are set to go. Thanks for joining us, and we will see you next time.